Welcome back, students, to the class on computer vision. And this time we will start the new chapter, which is on Hough transforms and to trying to find some pattern inside the images. So remember, till now we were doing a lot of things that were related to the image processing side of computer vision. For example, we tried to apply different types of filtering, and then we discussed the how to find the templates and the edges to extract them from the images. Now in this chapter we will be doing something that is more closely related to computer vision. So here we will try to find the patterns in the image. So for this purpose, we will be using Hough transform, and first thing that we will focus on will be the Hough transforms to find lines in the images. So remember, till now what we have seen is that we were we saw in the first chapter that image processing mostly deals with images and transforming those images into a modified image. For example, you apply the filtering on the image, you get another image. So that was image processing. But in the case of computer vision or vision related to the or the vision that in which you do some sort of processing, your goal is to find something interesting. So here we will do that thing. So this chapter, you can say, is the real topic related to computer vision. So what we want to focus, if you remember, we tried to use a little bit in the last chapter the use of we tried to see the use of templates. So here you see, for example, if we had an image of a car, we could use that image of the car in an attempt to find out if there is a car in the image over here. Okay. But there is another method that we can apply, is what we can say that we try to fit a model of something inside the image. So for example, my model, it is about a line. Okay. So I take a line, any line for example, and I can rotate it. I can put it straight, I can rotate it, and I try to put this line everywhere inside the image. Okay. Remember, the techniques that we will be using now, they are applied on the edges, not the original image. Okay. So for example, if this is your original image, we don't use this, and we use the image edges. So in the case of edges, we try just like we take a scale or a ruler, and we try to put it on the image everywhere in an attempt to find out if we can see a straight line. Okay, so this is the real stuff that we are interested in, finding the patterns inside the image. One pattern is straight line. So that's how we try to do over here. For example, in this image, this is the real one, but the edges of this image, it will give, for example, lines, lots of lines. Similarly, this idea can be extended in the future to find out other patterns or other models. For example, a circle. So circle is another type of model. Okay. So what we are effectively doing is that we take an idea which is with us, and we call that idea as a model. Okay. That idea, maybe it's a line, it's a circle, or it can be any other shape, a square, a rectangle, a triangle, any shape that's already in my mind, it's already with me, and we can use any size of that shape. The size is not a restriction, remember. Line, it can be any length, okay, and it can be any thickness also, it can be any length, And similarly circle, it can be a circle of any radius, any diameter. Okay, a small circle, a large circle, any circle, but it should be effectively circle. If I say circle, it is different from a spherical shape, or it's different from an ellipse. Okay, so like this we will be focusing on models. First model that we cover over here, this one is the line, and this idea can even be extended to the shapes that are irregular, that are not perfectly in the shapes that come in our that we call in general the geometric shapes. Okay, I hope the concept is clear. That's what we want to find. And how we find these things? We find these things by fitting the model inside our edge image. So if I want to find a line, it is effectively something doing like this. I take a scale and I try to find it everywhere. I try to rotate the line, this scale, and I try to fit it everywhere. Is it possible that I can find a line over here? Wherever I get a match, I will find it out. I will say that this is it. This is the output. Similarly, if I want to find out circle, so in that case, I will take circles of any radius or diameter and I will match it everywhere inside the image. Okay, this is what we want to do. Definitely it's not so easy job. If you think directly, it's not so easy. Why? Because there can be infinitely many locations where a circle can occur, and also the circle size, there can be infinitely many sizes of a circle. For example, a small circle, or maybe a circle which is very very large. Okay, and those circles definitely they can overlap. Here you see the circles that are far away, but they can overlap, they can occur anywhere. So you can see the challenge over here, because there can be infinitely many circles inside even a small image. Not so easy. Same is the case with the lines. How many lines can come over here in an image? Infinitely many lines, because line can have any orientation, any size, and it can be a slope, having a negative slope, positive slope, a line with a zero slope, just perpendicular to y-axis or x-axis, anything like that. So thinking it theoretically, if you think about it in detail, in a plain way, it's not so easy to detect any type of model. So such things that we want to find out inside the image, at one time we will focus only on one thing. Remember, either we focus on a circle or on a line or on a square or rectangle. At one time we will search for one thing only, and that one thing we call it parametric model. So parametric model, it basically represents a class of instances where each is defined by a value of the parameters. So it is something that we want to find inside the image, and it can be represented or it can be defined by some values of parameters. What does it mean? For example, line, it can be represented by these parameters where y equal to mx plus c. So this is a line, and what are the parameters over here? M and c. Any line you can define with these two parameters, m, slope of the line, and c, which is the intercept of the line. Clear? Similarly, you can define a circle with another equation. So where you will have the center of the circle, for example, and the radius. These 2 points. So maybe you can say center, which is an xy position, for example. On the plane you provide xy position, and then you provide the radius of that circle. This will give you the circle. So parameters over here, you will have three values: x, y, which is the center position, and the r value. So any type of parametric model you can try to find or search inside the image, edge image, and examples are like lines or circles, or even a specialized parameterized template or a shape, an irregular shape which is not a normal geometric shape. You can also find that. So how we find it? That's what I discussed previously. We try to fit a parametric model. So you choose a parametric model to represent. So you choose a parametric model to represent a set of features. So it represents a set of features, and what you do is that membership criteria, you don't keep it local. Okay, you can't tell whether a point in the image it belongs to a given model just by looking at that point only. Okay, so always if you want to find out, for example, a line, so you cannot say in the image that this pixel it belongs to a line or not. You cannot decide based on only one pixel. You have to see all the pixels that are coming in a sequence. Only then you can make a decision, one pixel it is part of a line or not. So remember, membership criteria is not local. You have to check out that all these points, they belong to a line. They belong to a straight line. All of them, they exist. In the edge diagram, in the edge figure, all of them they exist, then you can say that this is a line. Else it's not the parameter, it's not the line. Computational complexity, it's very important over here, because remember this technique that I told you, even if I give you some method, if I give you a scale and I ask you that there can be many lines, and you have to search all of them, it can take too much time. Practically, if you start it in a sequence, it can take exponential time, too much time to find out all the lines. Given that computers, they don't think like our brain. Our brain, they can think, but computers, they cannot think like this. They have to check everything one by one manually. So in that case, overall, the computational complexity of such fitting the parametric model, it is not less, it's a lot. So it is not feasible to examine all the possible parameter settings, all the possible lines that are possible, you cannot search them inside the image. So practically, this approach will not work, that you take a ruler and you try to find out all the possible lines that can exist in the image, because there are practically infinite number of lines possible. You cannot check all those lines. It is not feasible. So here you see some examples. So here you see, for example, in this circuit diagram, there is a line, there is another line, or maybe you can say these are set of lines, another one. Likewise, there can be many different lines. So how you will decide it that a line can exist over here, that's a big challenge, and that if you try to do it with some traditional approaches, it will take extreme amount of time, too much time, beyond the capacity of a normal computer. So you see over here that it will always be a straight, it will always have a defined orientation. Line is always straight, yes, but you don't know what will be its orientation. So for example, here you see this line, it's a little bit slanted. There is another line over here with a different slope, another one different slope. So there can be infinite number of combinations of lines that can be possible. So how to search them? So how you will know that a line exists? So you try to make a line and then try to see if a pixel exists on every all of these locations in the edge image. If there is an edge pixel everywhere over here, then you will say that this is a line. So it is not so easy. For this, we will be using some different approaches. Why the line fitting is difficult? So there are some problems with the line fitting. We will see the main three, or the main are three of them. One is extra edge points. Remember in the last chapter we saw edges, we discussed them, edge detection, and overall the result of the edge detection process, like canny edge detection, the results are not so smooth, not so perfect. Always you take any edge detection method, because it's based on derivatives, and it will take the image and try to transform it. It is not perfect. Always there are some deviations in the result. So what can be the deviations in the result? So sometimes there will be extra edge points, we can call them clutters, and the multiple models. For example, if you see over here, there is some sort of line. On the end of this line over here, you see this is a cluttering. Cluttering means grouping. Okay, so the word clutter is like grouping. So there are lots of pixels at one location, and it occurs because of so many reasons we saw in the last chapter. Either the brightness is not correct, or the image, the angle from where you are taking the image, it's not proper, or there is some shade that is coming on that place. That's again related to brightness. So there can be so many things that can cause the cluttering in the edge image. Okay. Another problem in the line fitting that can come is that only some parts of each line are detected and some parts are not detected. So if you see over here, there is a line over here, and suddenly at some places the line is broken, not smooth. And if you remember, in the last chapter we saw for the canny edge detection that there were two parameters given for the canny edge detection. One was the lower limit for the threshold and the upper limit. Upper limit of the threshold was used to decide if we have a new edge. So if the value of the pixel was strong enough, we consider that maybe this is a new edge that's starting. And then we continue with the lower threshold value, we keep on continuing that edge or that boundary. So here what happens is that it is possible a lot of times that because of all those reasons related to the image and brightness, lines are not detected, the edges are not fully detected. Sometimes there is an edge, sometimes it's broken, it's not there. So in that case, how you can fit a line? That's a big problem. Third reason that is very common in the edge images is the noise that occurs in the edge points or their orientations. So for example, if you see over here, this is a line. All of us know that this is the line that represents the edge or the boundary of the building. So it should be a straight line, but practically there are always ups and downs. So it is never the case that you will get a perfect edge. Again, for same reasons like brightness, image orientation, and the other types of discontinuity, you will see that the edge that we detect, it's not perfectly straight. There are always different types of noise. So with these three big problems, now think in your mind, can we take a scale and we try to find out a line? It will be a very difficult task if we do it using a normal approach. So it's a big trouble. Okay, so pause over here and try to focus and the importance. What we are discussing over here, we want to find out some information from the image. That is the reason we study computer vision. That computer vision is trying to find some information from the images. And the first major type of information here we focus on is to find out, for example, some types of parameters in the images if they exist, like the lines, or in the future we can extend it for circles or irregular shapes. So there are problems. It's not so simple with any traditional approach. It will be a nightmare to do this. And these are some of the problems that occur because of the edges. The edge diagram or edge image is not so clear. So for this purpose, we use a a different approach. So this approach will be totally new for all of you, and it's quite a unique approach, and I wish we were in the class and I could explain over there. And this is one of the most difficult chapter till now. So to explain the voting, I will have to go and first of all explain to you the concept of the lines and the the image space and the Hough space. Okay, so let's say you have a line that you represent in your normal Cartesian plane. Remember your Cartesian plane in your colleges, even in schools, you study graphs, geometry, and over there somewhere in the graphs you study that there is a xy plane. On one side you have the x, other side you have the y, and you can represent any shape on this graph, and especially we are interested in making lines on this graph. Normally this type of graph is called as this type of area where you draw the graph, it's called Cartesian plane. Okay, so xy Cartesian plane. For our field over here, because we are dealing with the image, remember our images, they are also represented by xy dimensions. Okay, so one dimension is x and another one is y, so it is also exactly same as any graph. Okay, any graph paper, same thing over here also for us. So let us say we call this Cartesian plane, for us we call it image space. Okay, so it's an image, and on this image we did from the last chapter, we convert this image to the edge image, and now it is in the form of an edge diagram for us. Okay, so on this image we have got, for example, a straight line. Okay, so we have got over here a line on this image space. How the line is represented, we just discussed before. A line, it is represented by this formula for a linear this linear equation. It represents a line, and this formula over here is y equal to mx plus b or c. Okay, where m shows us the slope of the line and the b represents the intercept of the line. So if you, those of you who don't remember, just I will repeat it. M means the slope. Slope is this thing. For example, this slope over here, this line is positive slope. If the line is like this, it's a negative slope. If the line is something just like flat, then there is zero slope. And what about this? Anyone remember? If the line is like this, just parallel to y-axis, then it is infinite slope. Okay, so this is the slope m. And the second thing, so any line you can represent over here with this slope. For example, line like this, like this, like this, any line. Okay, another thing that line can have, that most of the lines, they will not be passing from the origin, not from the zero. Okay, so if the line is passing from the zero, then you can represent that line by these two things only, y equal to mx. Okay, but if the line is not passing from zero, it cuts the y-axis somewhere else. So it cuts over here, for example, plus 5, or it cuts over here, for example, the y-axis at minus 3. So in that case, you will be using the second parameter. It's called the intercept. Intercept is basically the y-intercept, where this line is cutting the y-axis. So if it's cutting over here, then you will use, for example, mx, whatever is the value of mx plus 5, or you will be using the value of m times x minus 3. Clear? So this is it. This is the representation that we have got. We call it the Cartesian plane representation, or it is in our case the image space representation of a line. Now let us suppose, just imagine that if you see over here, you have got the x and the y, okay, and the two unknowns that we use to represent the line over here is the m and b. Let's suppose in another form of representation, instead of x and y, we put m on the x-axis and b on the y-axis. Okay, what will happen in that case? Okay, so let's say your equation for line is y equal to 2x plus 3. Okay, this is your line. So it means the slope of the line m is 2 and the intercept is plus 3. Okay, so what you want to do is that you want to represent it in another form. Why we want to do it, we will discuss. Okay, and what we do over here is we represent it in the Hough space in another form. We represent it by using m on one axis and b on the other axis. So for example, m is equal to 2, so this is the m value, and on the y-axis we have b, which is, for example, in this case 3. So for the value of m equal to 2 and b equal to 3, we have got over here a dot. Okay, it's not a line, it will be only a dot, because for one particular value of m and b, I will get only one dot. Clear? So what effectively is happening, that a line in the normal image space, I can represent the same line over here in the Hough space or the parameter space as a dot. Okay, so feel free to pause the video, think over this concept very carefully, very important concept, that over here this is a new type of representation. We can call it the parameter space, because this representation is based on two parameters, m and b. Remember, previously we also discussed, we called it a parametric model because it's a model that that represents that uses two parameter values to find out a particular instance inside the image. So here we have got these two parameters, and with the parameter I get one dot inside this type of representation. So if there is another line, for example this one, so it's for example, if you see this line is almost, it's parallel to that one, so the slope is same. So for example, that line, the slope was 2, this is also 2. Okay, slope is same, so m will be 2, but this line, maybe it will cut the y-axis at 0. So this is another one. No, not over here. Sorry, it will cut, m will be 2, b will be 0, intercept will be 0. So the line will be here, the dot will be here. So you saw over there one dot, over here one dot, and you can keep on changing, you can get other such dots. Okay, so if I have another line like this, maybe its slope will be here. Is it clear, the idea? Every line over there, it will be representing one dot over here. So this is just giving you an idea. A line in the image space is a dot in the parameter space. That's given over here below. A line in the image corresponds to a point in the Hough space. That's a very important point. If it's not clear, pause here, discuss with each other, ask me in the group, and then you continue. Okay, so the Hough space, we try to do it, and uh, what can happen, what next can happen. So let me delete it. Okay. So what next is, um, let's say on the image space you have a dot, not not a line, only a dot. So what happens for this dot? Okay. So I've got a dot over there. What do you think? What do you think? What type of line can pass through this dot? So I put over here a line. This line passes through the dot, yes or no? Yes or no? Yes, this line passes through the dot, so it will have some slope and it will have some intercept. Okay, so let's say this is over here. Just giving an example, I don't have some concrete. There will be one example coming, a concrete example. This is just a toy example over here. So this line, it is represented in the Hough space over there by one dot. Yes. Now let me draw a variation of this line. It changes another but passing through the same dot. So in this case the slope is changed and again the intercept will also change. Yes. I draw another one, another one, another one. So all of them, they will have a different value of M and B. Is that clear? But finally all the dots, all the lines that are passing through one single dot. One interesting thing that is about those dots will be that they all these lines that are passing through one single point, they will occur on, if you plot them in the Hough or parameter space, they will occur on a straight line. So what's the take home point? What's the important point? If you have a point in the image space, that point can be represented by, because infinite number of lines can pass through this dot, this point. So that point in the image space, it can be represented by a line in the parameter space. All the points, all the values of M and B that occur on this line, they will satisfy this point. They will represent a line that will pass through this point. So it is very take home point. If it is clear to you, very important for you, very important to understand. In the Hough, in the image space, if there is a line that is represented by a point in the Hough space. Hough space is another name for parameter space. And if there is a point in the image space, it is represented, it can be represented by a line in the Hough space. Very important point to understand. So these things are interchangeable. Line in image space is a point in Hough space, or a point in the Hough space is a line in image space. I hope it's clear. So take your time and go through it. If you have questions, ask. So this is what we want to focus, why we want to use it. So what's the reason? That we will now discuss next, why we do this. So for now, the summary is that in the case of image space, for any straight line y equal to mx plus c, there are many lines passing through the point, for example any point. Okay, and common to them is that they satisfy the equation for some set of parameters m and c. So this is the opposite case they are explaining. For any point in the image space, you will have infinite number of points that can satisfy this point. So that's what is shown over here. So common to them, all those lines that are passing through a point xy, is that they all satisfy the equation that will have a parameter mc that occurs on a straight line. So here is an example. So you see over here lots of lines, y equal to minus 1 x plus 0. Then there is another one, y equal to 1x plus 0. Then there is a 0.6, m is 0.6 and b is 0.4, m is 0.8 and b is 0.2, and so on. There are so many points. All of these points, yeah, when you take it, so they are passing through one dot, which is 1 comma 1. Okay, so for this, when you plot it, you will get a straight line representation. So let's say I don't have another graph. So let's say I make the graph. I don't want that this confuses you. This is the image space. I use the same scale over here for the Hough space, and here it is. Let's say, but they are using negative values. Only one of them negative. Okay, so I think it's manageable. So let's say this is my M for my drawing, and this one is B or C, whatever you call it. Okay, so in that case over here, I will take this one. M is 1 and B is 0. So M is 1, this one, and B is 0. So this is my point number 1. And let me change the color. No, again, don't want to use any color that's already on the slide. Maybe green. So this is 1 point. Okay, and the next one is point 6. So it will be difficult. Point 6 maybe somewhere here, and point 4. Okay, then is point 8 and point 2. Point 8 here and point 2. And then it is m is 0 and y is b is 1. Okay, and can you see the pattern over here? And then this was m is minus 1 and m is 0 and y is minus 1. M is minus 1, minus 1 and 0. So here it is, m is minus 1, this one was 0, m is 0 and b is 1. I did a mistake. Yeah, I messed it up. Let me do it again. Let me start from this side. M is 0 and B is 1. So it is this point. So I was wrong. So this one is done. Then M is 0 and 1. And then it is M is 0.8 and B is 0.2. 0.8 is this one and 0.2 it's almost here. Then there is another one, 0.6 and 0.4. And then there is M is 1 and B is 0. So it's this point. So this are done. then m is -1 and b is 0. There is a mistake on this slide, I think. Yeah, yeah, they are making me crazy also, because if you look over here, that's my thinking. Which line is this? Slope is 0 and this over here intercepts at 1. You see, it intercepts at 1. And this is the line over here. Slope is 1 and it intercepts at 0. You see, intercepts or cuts the y-axis at 0. This is another one and another one, and by that rule, this line over here, it is intercepting at 2. So this is a mistake and they are making me crazy. Okay, so it's a 2, not 0. So slope is negative, you see. It will be -1, I don't know. It's possible it will be -1, but intercept is definitely 2, it's not 0. So correct it up. So slope over here, m is -1. So -1 is somewhere maybe here against this. This is 1, so this is -1. And intercept will be 2, which, so the point is this thing. So you see over here, this is a pattern that's occurring. Practically all the points, infinite number of points that occur that can pass through in the image space, that can pass through this location 1 1 1 comma 1, x is 1 and y is 1. All the lines that can pass through this point, they occur on this straight line in the Hough or the parameter space. So this is it. I ask you to seriously think over it. Take a graph paper and try to make one such yourself. So let's say I give you another point. So I give you a line, for example, you take this point. Okay, so which point is this? 1 comma 2. Now you practice with 1 comma 2. Try to draw the straight lines. Different types of definitely there can be infinite number of lines passing through this. Okay, you cannot draw all of them. So try to draw only the important lines that pass through it, and only draw those lines that are cutting, that have some slope, that have an intercept you can know easily. For example, it is cutting the y-axis at 2, at 1, at 0, like this. Okay. And second thing, what about the slope? How to find out the slope? Slope is basically, what does it mean? How you know this is a 1 slope and this is a 0.6 slope or 0.4? Slope is basically, what does it mean? It is basically the change in y divided by the change in x. Okay. So slope you can find out yourself when you draw a line. First of all, you draw a line with a with an easy intercept, and then you try to find out, for example, for this line, okay, this is the line. I will try to find out that if my line changes from here, so this is the starting point 0, from 0 until 1, how much is the change? 1 unit is changed. Okay, so during the period when, so this is delta x, change in x. Okay, so during the period when x has changed 1, how much change occurred in the y? So in this case, if you see clearly, the y is also 1. So that's why the slope for this line will be delta y over delta will be 1. For some other case, it will be a different value, and you have to use a calibrated graph. A graph paper, use a graph paper where you have got these boxes already on the paper. That will help you. Okay, so for this over here, for example, this line, so in this case, for example, the delta x, it's given by 1, and when you have this thing which is given by 1, at that time how much change in the y occurred? It is this much. So how to know? This you should know from the graph paper. So for example, I think in this page you have got 5 boxes in a one, so this over here represents 0.2. So the change that occurs overall, it is 0.2 divided by 1. So for this line, I don't know where they represent it. So it is 0.2 and yes, practically it is 0.2. Yes, I don't know. They have messed up over here, or I don't know what they did. Maybe these values are not correct, because 0.2 they have written it over here with the intercept, which is not a good thing. Does it cut this line? It is cutting the y-axis at 0.2? No. So there is big problem with this diagram, the values of this diagram. So try to make it yourself a separate one independently, and don't accept the values which are like this. Always challenge whatever you see. Okay. So the slope over here for this line is coming as 0.2. Okay. And the intercept, which is, I think they have written in the opposite, intercept over here is coming as 0.8. Okay. So this is it. This is how you will find out. And I ask you all that you take this point. This is the example that I gave you, 1, 2, and you try to draw it, the half space for this yourself practically. Okay. Very important. I don't know, but maybe you can get an exam question like this. It is highly likely, it's possible you can have any such question. Clear? So this is it. So in the half space, what happens is that practically the equation that you saw previously for the line y equal to mx plus b or c, you can rewrite that equation like this. Okay. So you can rewrite the equation. Why they rewrite it? They rewrite it in this form because now we can consider x and y as parameters and m and c as variables. Okay. Now you can use them to draw the points or the lines in the half space. So basically the theory is same that I gave you before. So this over here represents a line in the MC space. So another name for the parametric space, so a typical exam question, parametric space is also called as half space. It is also called as MC space. Okay. When we call it MC space, now the parameters or the values that change in that space, the values that change are x and y. Parameters are there. So a single point in the xy space, it gives us a line in the MC space. So for example, if you have another point x and y, it will give us another line in the MC space. Now this is a very interesting thing. Let's say you have 2 points over here in the MC xy space. Okay, image space, you have got 2 lines, or you have got 2 points. One point is over here and one point is over here. Okay, just ignore the line for now. We only focus on the points. So what are the point coordinates? One of them is 0, 1 and the other one is over here, which is 1, 2. Okay. So these 2 points, what we do over here is that if you take this point and use the same practice you saw previously, this point over here, because it's xy space or image space, the point here, it is represented by the line in the half space. Another name for half space, they are sometimes also calling it AB space or MC space, but I prefer MC. Don't use AB, leave it. MC is enough. Okay. So a point over there in the image space is a line over here in the half space. Okay. So this is one line, this one, and then there is another line that is represented by another point. Clear? So now the important thing is these two dots. Remember, if you have in the image space or in the Cartesian plane, if you have 2 points, you can connect those 2 points to create a line. Remember? So the 2 points, you can connect them to create a line. So when you create a line, that line again, it can be represented by a point. So a line over here is this, its formula is y equal to, for example, 1x plus 1. So that line is represented over here by this point. Okay, and the interesting thing that I wanted to focus over here is that the line that is connecting these 2 points, that line will be the intersection of the lines that were representing 2 points in the image space. So remember, you have 2 dots or 2 points in the image space. These 2 dots are represented by 2 lines in the Hough space. Those 2 lines in the Hough space, wherever they meet or intersect, the point that you get over there, that point can be represented back by a line in the image space, and that line will be the line that passes through both those points. Lots of theory. So you can pause it over here, think over it. If you are not satisfied, go back, just replay this video many times. I hope it will absorb. Okay, so the concept over here that I'm giving over here is points. I convert them to lines. Okay, those 2 lines, they give me another point, the intersecting point, point of intersection, and that point of intersection is basically represented by a line, and that line is such a beauty that that line must pass through those 2 points that we saw earlier. Is it clear? So this is it. Make sure you understand this thing, and this is one important concept that we use further. You can pause the video and go and take something to eat so that your brain becomes more active. Take some sugary stuff, some glucose, so that your brain becomes more active, and try to come back and try to absorb these things. So 2 points. So that's the theory that I gave you now. The concepts that I gave you now is this is the theory. 2 points you saw earlier in the last slide. Any 2 points over there, they have given the numbers. So for example, the 2 points are x1 and x1 y1 and x2 y2. These 2 points, they will create a line in the xy plane. Okay, so you have 2 points. Those 2 points, they can be used to create a line in the simple xy plane. We are not talking about Hough space for now. And these 2 points, they can give rise to 2 different lines in the MC space. Okay, or the Hough space. So in the MC space, these 2 lines, they will intersect at some point, any point, for example, A prime, B prime, and that point is where the M prime is the slope, and C prime, for example, will give you the intercept, and it will give you a line that will be represented, that will be defined by same original points, x1, y1 and x2, y2 in your xy plane. The fact that is very important is that all the points on the line that are defined by x1, y1 and x2, y2 in this xy space, they will have the lines that will intersect at this location in the MC space. So all the points that occur on this line, all the points that occur on this line, okay, all of them, they will be represented by different types of lines, and all of those lines, they must pass through this point of intersection. That's the important point. All those will pass through this point of intersection. Is that clear? So points that lie on a line, they will form a cluster of crossings. So all of them that are lying on a line, they will be creating a intersection point or a cluster of intersections on in your MC or Hough space. That is what is happening over here. So again, from another angle, the same concept is given. You have got a dot over here, a point in the image space. It is represented by a line in the Hough space, and you see the formulas. You have two dots. These two dots or 2 points, they will be represented by two lines in the Hough space. And the interesting thing is that these two lines, they will intersect exactly at one point only. They will only cross at one point, and the point where they cross, it will be the line that is passing through both these points. Is it clear? Very important thing, very important point. Okay. So how we can use it? So till now we have seen some very interesting theory, lots of important concepts, but why we study it? Why? So how we can use it? Remember what we were doing? We were trying to find out parameters from the image, and the parameter we focus now is the image, the line parameter. So how to find this line from the image? That's an important question. So for this purpose, what we want to do is just take an example. Let's say this is your image, and inside the image, this is your edge image, and inside the image you have got these pixels that are representing some edge. Okay. So let each pixel in this image, so this is your, these are the edges, these are the dots. Now these points over here, try to use them, each point, it will be representing a line in the Hough space, remember? So each dot is representing one line. Okay. What you can do is that, because remember we discussed previously in the theory, we saw that the edges, they are not perfect. They are not in a straight line. If they are in a straight line, then the half of the story is easy to solve. Okay. The problem with the edges is there is noise. Sometimes the edges are not there. There will be so many problems, and sometimes there will be so many edges in a cluster, cluttering. Okay. So all these problems, to solve it, what we do is that we take each pixel, each point, and we plot it on the MC plane or Hough space. We use a line for each of those points. Okay. So we take a point and we make a line for it. Now because they are not on a straight line, so they are not on a straight line, there will be differences. So they will not pass from a single point. They don't intersect at a single point. Is it clear? Very important. They don't intersect at a single point, but if somehow you become less strict, so let me change the color. Okay, maybe this is okay. So instead of having a point, instead of looking for a single line that represents these set of values, these pixels, if you try to make a you imagine that you try to imagine a big box, not a small one. Okay. instead of considering a small point which will be the intersection of all those lines, which is practically not possible, you just imagine a big box that collects the intersection of all those points, all those lines. All those lines, wherever they are meeting or intersecting with each other, they occur inside this box. Okay? They occur inside this box. So in that case, you take this box at the end of this process, you decide to make a line that is the average of, for example, this box. So let's say the m value for this box average, maybe this is 3 and this is 4. You take maybe 3.5. Same is the case over there. Maybe you have got 1, 2, 3. So again it is 3 and 3.4. So you select a value which is in the middle, 3.5 for the slope also. Okay. So what will happen? What will be the result? The result will be a line which does not represent all of them perfectly, but it will be very, very close to all of them. Very interestingly, it will be very close to all of them, but it will not represent perfectly all of them. A lot of the points will occur on this line, but a lot of them will not occur on this line, but they will be very close to this line. I hope it's clear. Very important point. That's the summary of this chapter. So what we do in Hough algorithm is that we let each edge point, each point over here that is representing an edge. So each edge point in the image space, we let it to vote for a set of possible parameters. So every edge over here, it is voting for the a set of possible parameters. So the parameters, instead of having those values as continuous, so continuous values we can't trace them. Okay. Instead of having continuous values, we choose discrete values, 3, 4, 5, 6. We don't consider values that come in between. Okay. So what happens is that each point is represented by a line, and wherever that line passes, each parameter. So the previous approach that I gave you, you make a window and you select all the intersections that come inside. But practically how it is done, it is a different method. Practically how we do is that each line, it will vote from the from where it is passing, for each bin from where it is passing. Each of these boxes, it is called as a bin. Okay. Okay. Each of them is a bin. So we define discrete or countable number of bins. Okay. So we start, and there are lots of bins on this screen. From anywhere the line is passing, it will add a vote. Even if the line is passing a little bit from that bin, it will put a vote over there. So for example, this line over here, it is putting a vote for these. So let me erase it. Okay. So this line over here, the first one I take, it is putting a vote over here for all these. So where else? Maybe this. It is putting a vote in all these cells, and it is infinite, far away. Practically in the algorithmic level, you don't go up to infinite, but you go to some very large value. Okay. So it puts a vote over here for all these cells. So these are a lot of cells, but practically still they are a very few numbers. You see all of these cells above, they have nothing to do with this line. So they will be just ignored, nothing. Now another line comes, and another line will select a different set of. So I select this line, for example, this one, a vote here, another vote here. So it will practically add the vote in the previous count. So each bin has got a vote count. So it will just increment that vote. and here and here. Okay, so you see practically this line over here, it is adding the votes only in this in these sets, these set of bins, whereas that one was doing in this direction. Now let's say I have got another one, and this time I choose a different one, this one. Now this one is adding a vote over here. For this, let's say it's not passing from this one, so I will put a vote over here, and what about this? Yes, over here also, and here and here. Okay, so I think 3 is enough for our demonstration purpose. So practically what happens at the end of this process, this bin has got, so this voting will be done for all the possible set of values, for all the possible set of pixels. How many pixels can be there in a straight line? For a smaller line, maybe 10, 20 pixels. For larger lines, maybe 50 or 100 pixels. But this is nothing. For computer, it's not a big deal. Okay. So it will create the this whole grid will be tracing the number of it will have a large number of bins, and each bin is representing a set of values for M and B. So there will be a voting overall, for example, and at the end of the process all these bins will be counted. For example, this just say 1. Here you have 3 votes, here you have got 3 votes. Okay, here again 3 votes, 1 vote, 1 vote, 1 vote, 1, 1, 1, 1. Here I have got 3 cells which have got similar voting, but practically what happens is that when you will be doing this thing effectively for all the pixels at a practical level, at that time lots of lines will be passing through one of them, and one such cell will get considerably big number of votes as compared to other cells. Okay, so in this case it is this cell over here. This cell, it will get at least much bigger votes than all of its surroundings. Okay, even if it's not bigger, not too much bigger, but still it will be, for example, a little bit big. Maybe it is 50 votes in this cell, maybe the surrounding is 45 or 40. Still you will choose, for example, the biggest value. So this overall is the process, we call it the voting process. So in the voting, what happens is that in the normal voting in the elections, people, for example, in the case of Shura, people go to a place and every person, he goes over there, and out of 6 or 7 candidates, he selects, for example, he says that for me, I like that person. Another one comes, I like another person, and so on. At the end of the day, at the end of the voting day, the votes are counted for everyone, and then the one who has got the maximum number of votes, that is elected. Okay, same is happening over here. Instead of me trying over here to fit a line, okay, what we do is that we ask them, the pixels, okay, pixel number 1, what you think, which one you like over here, which one is the line that represents you. So pixel will tell you all those lines in any angle that is passing through this point. Okay, so it will give a 1 1 1 1 for all the lines that can pass through this point. Number 2 point will give another set of values, and they will have different values, but they will converge only on one line that is closest. Remember, there will be some differences. Okay, for example, this one is not on this line. Still, because the bin size is bigger, it is representing a big area for 3 to 4, so it will be automatically covered in this thing. or it will be the closest. Okay, there will be mistakes also. For example, this bin has got 45 votes, the closing one, if the line is not so straight, the closing one will have 30 or 39 or 40 votes, so it will be close. But practically, if at the end I make a line, maybe that line does not represent this pixel, but it is very close to it, not so far away. Clear? So this is the process of voting that we discuss over here. So what we do is that we let each edge point in the image space to vote for a set of possible parameters. So they are voting in the whole Hough space in all the set of bins. And all those votes, when they are accumulated, accumulated means like calculated, or you make a sum of all those votes in discrete set of bins. Remember, if the bins are not countable discrete, then the voting is not possible. Why? Because they will be giving the values for infinite number of different floating point values. So for example, one value is 3.4545 and it's continuing. Another one is another one. No 2 points they can match, they will be different if it's a continuous value. That's why we said initially that it is basically the bins that we use for voting. Okay, we have some fixed number of candidates, not infinite number of candidates. Same like in our normal elections, we have 9 or 10 or 12 fixed or countable number of people, discrete number of people that we have to choose from. So the points have the choice that is fixed. They have to choose amongst these bins. They don't have anything outside this area. So they have to choose, and parameters with the most votes, they indicate the line in the image space. Clear? So this is it. Let's go back and see the theory we left before. So this was it. We wanted to discuss the voting. So practically it is not feasible to check all possible models or a combination of features by fitting a model to each possible subset. So I told you, if I give you an edge image, you cannot take a scale and try to find out in all the orientations, in all the directions, you try to find out and match a line, because there can be infinite number of possible positions for a line. It can be infinite number of line length and infinite number of line angle. So for that purpose we use this method, which is more efficient and very, very practical, where we use the voting mechanism. And voting is a general technique where we let all the features, so all the pixels, to vote for all models. So by model we mean over here our line parameters. So they vote for all models that are compatible with it. So the features, they vote for the MC values that they like, and you cycle through all the features, all the pixels, all the edge pixels, okay, and each will cast a vote for the model parameter, and at the end you will look for the model parameter that receives a lot of votes. I hope it's clear. So all the three problems we discussed previously, if you remember this one, these three problems are still in the edge image. So there will be noise in the edges, there will be discontinuities, so only some part of the line is detected, some other is missing, discontinuity will be there, and there will be cluttering or some extra edge points. All these problems are still there. They will also cast their votes, but typically their votes should be inconsistent. Remember, they are casting a vote, but their vote will not have a specific pattern. They will not choose a particular MC value. So their votes will be inconsistent with the majority of the good features. So the good feature votes will always be more than the votes of the noisy pixels. So it is still okay. Again, the second problem, it is still okay if some features are not observed, as the model can span multiple fragments. Some pixels are missing, still you will be able to make a line because the other pixels, they are voting and you can interpolate the line. So to fit the line, what we need to do is we need to answer a few questions. You are given points that belong to a line, what type of line it is. So here it is, these are the points given. In normal technique, it's not easy to find it out, but here with this technique, the voting technique, each point will vote and we can judge. Another problem that the voting solves is that how many lines can be there in this image. So in this image, maybe there are 20 lines or 50 lines, I don't know. But by the voting technique, automatically it will be found out. And the important thing is that each point belongs to which line. The points, they will themselves decide where they belong to. So Hough transform is basically, what is the definition of Hough transform? Hough transform is a voting technique that can be used to answer all of these main ideas. So each edge point, it votes for compatible lines and it looks for lines that get many votes. That's the summary of Hough transform. It's a voting technique basically. So this is the theory we saw. It all starts with the image space and the Hough space. And remember what we discussed is that a line in the image space is a point in the Hough space, and a point in the Hough space, a point in the line space is, a point in the image space is a line in the Hough space. So we discussed this theory. So if I have got a point in the image space, infinite number of lines can pass through that point, and those lines, if you plot them in the Hough space, they will represent a set of dots, and all those dots, they will occur on a straight line. And then we discussed that if you have 2 points in the image space, those 2 points, they will be represented by 2 lines in the Hough space, and the line that is passing through those 2 points, that will be represented by a point in the Hough space, that is the intersection of those 2 lines we saw. So this is the theory we have seen, and we saw it practically. We use it in the Hough algorithm. We use this voting mechanism, and each of the pixel votes for a discrete bin, and at the end the votes are counted, and the bin with the maximum votes is selected for the best values for the line. So the important thing is that line representation has some issues. I think let's take a break. I think next time I will go through these issues, and we will go to the next polar representation and also the lab work. We will